Alright, so this video is on logarithmic differentiation. So logarithmic differentiation is going to be our last differentiation technique or method, and from here on out the rest of my videos involving differentiating will simply be applications of the rules you've learned prior. So we'll start with some refreshers. So by this point you should already know how to differentiate natural logs, even with the use of chain rule. But if not, this probably isn't the video for you. So let's go ahead and take a look at a couple examples. So we'll start out with f of x is equal to the natural log of sine of x. Now if we were to take the derivative of this, we traditionally know that there's going to be some chain rule involved because we don't just have ln of x. So for our f prime of x, we're going to have to do the outside. So that's our 1 over sine of x. And then multiplied by the derivative of our inside, which would be cosine of x. So you'll end up with cosine over sine of x. Alright, another example, we have the square root of ln of x. Okay, so there's actually two different ways to solve this, but we're going to go with the traditional chain rule way, just to give you an idea of where we're headed with this video and how things can be a little bit more efficient. So as you know, a square root can be written as a 1/2 exponent on any term. So we have ln of x to the 1/2. If we were to differentiate this, our outside would be that exponent. So we're going to have to bring down that 1/2 while keeping the inside the same and using our power rule, so subtracting our exponent by 1. So it'll be 1/2 times ln of x to the negative 1/2. Alright, and then multiply by the derivative of the inside, so ln of x, which would be 1 over x. Now the way we can rewrite this to clean it up a bit is if you remember a negative exponent, so that is our minus sign right there, means that our term can lie on the bottom of the fraction with the regular exponent. So this would actually be the same as 1 over 2x times the square root of ln of x with all of our terms combined and simplified. So those are two examples just to review differentiating logarithms in general. Now I'm quickly and briefly going to talk about the formula for differentiating regular logarithmic functions. Now that's going to be later in the video, but I want to note that when I use the term logarithm, I am typically referring to natural logarithms, as you will find that they're used a lot more often in calculus. Now this is also why I'm not going to spend much time on the regular logarithm, but this is the formula for differentiating the traditional logarithm. Now the form of a traditional log is log base b of x. Alright, so this base is going to be some number, and then x is going to be some sort of variable or value. So if we were to differentiate log base b of x, so our d of dx, just saying that we're going to be differentiating it, the derivative of this would be 1 over x times the natural log of that base. So if we add an example, we'll say f of x is equal to log base 10 of 2 plus sine of x. Alright, so if we're going to take the derivative of this, right, it's going to be our well, as you can probably tell, we don't just have an x in here. So there is going to be an element of chain rule. And I know that may be harder to spot out because you're not used to this rule. But I can guarantee that you're probably not going to see this very much in your Calculus 1 class. You may see a question or two, but typically we're working with natural logs. So anyway, following this law, it would be the derivative would be whatever's on the inside right here. So we have our log base b of x. When we take the derivative, that x comes out on the bottom. So this, our 2 plus sine of x, is going to be there at the bottom of our fraction, right? And then it's multiplied to ln of the base. So our base is still 10. It's going to be multiplied by the natural log of 10. Now the last part is that because we don't just have log base of x, we have log base 10 of 2 plus sine of x. We're going to have to do some chain rules. So we're going to have to multiply by the derivative of this inside. So our 2 would go to 0 and our sine would become cosine. Then that would be our final answer. So now that we've got that out of the way, let's talk about the meat of this lesson. Simply put, logarithms allow us to simplify equations before and during differentiation, or to differentiate previously undifferentiable equations. So we'll start with the example of simplifying equations. Now say we had f of x. Now let me separate this from everything else. Now say we had f of x of ln, so our natural log, of x plus 1 over the square root of x minus 2. Now you may be tempted to differentiate this right off the bat, and if you notice, it would require both chain rule and quotient rule. You'd first have to do the outside, which would be our natural log, so you'd end up with 1 over this whole mess, right, which would essentially just reverse the fraction. But again, initially 1 over this fraction, right, multiplied by the derivative of the inside, and the derivative of the inside would be quotient rule. So you'd have a whole big mess to take care of. Now using natural logarithm laws, we can simplify it first and make it a little bit easier to differentiate. Now you've probably learned these laws in previous courses, but they're incredibly useful when it comes to logarithmic differentiation. So I'll go ahead and write them here. Now if we have the natural log of any value a with an exponent b, we can rewrite that as b multiplied by the natural log of a. So essentially, you can take whatever exponent there is on a term in a natural log and pull it out to the front. So next, we have the natural log of a times b. Now, there's an additive property to this. We can actually separate any two terms multiplied by each other within a natural log to be the natural log of the first one plus the natural log of the second one. Now our final rule is that if you had the natural log of a divided by b, you could separate that into the natural log of the numerator minus the natural log of the denominator, right? So these are the three laws that come in handy. Now, those will make it much easier to take the derivative of this function. And you may notice right offhand that our third law definitely applies here. So we can actually rewrite this as the natural log of our numerator sorry about that, minus the natural log of our denominator. Furthermore, to make it even easier on ourselves, because if you notice here, we're going to have a little bit of nested chain rule, right? We remember that our exponent for a square root is 1/2. So this would be the same as saying the natural log of x minus 2 to the 1/2 power. Now, if you remember, by our first law, we can go ahead and pull that exponent out front. So once we've completely rewritten this whole thing, we'll have the natural log of x plus 1 minus 1/2 the natural log of x minus 2. Now when we take the derivative of this function, it's going to be our f prime of x is equal to, well, we know by natural logs we're going to have 1 over the inside, so our outside multiplied by the derivative of the inside, which would just end up being 1 anyway. So we'll have 1 over x plus 1 minus 1/2, then derivative of the outside, so it's going to end up 1 over x minus 2 multiplied by this 1/2. So to simplify it real quick, we'll have right there, and then our chain rule multiplied by the derivative of the inside, which would just be 1, so it doesn't really matter, and this is our final derivative. Now, here's where logarithmic differentiation gets a bit more complicated. There exists instances where we can take the natural log of both sides of an equation in order to be able to differentiate a problem that may have previously seemed undifferentiable. So to start off, the actual method of logarithmic differentiation follows the following form. We have y prime is equal to y times ln of y prime. In other words, the derivative of ln of y. Now, it's up to you whether or not you want to simply plug in your values into this formula, or if you want to execute your problems using the logarithmic technique. But for the sake of this video, I'm going to show you the execution, and then I will tie it into the formula at the end of each problem. So let's start with this problem. Say we had y is equal to sine of 9x to the ln of x power. Now we don't actually know how to differentiate anything to the ln of x power, right? So here's where it comes in. Now I'll show you how this formula works in a second. Let me block that off. But as for the actual execution and getting to this point, you take the natural log of both sides. So we'll have the natural log of y is equal to the natural log of sine of 9x to the ln of x power. And you take the derivative. So if we take the derivative of this side, we're going to have our 1 over y, and then multiply by the derivative of the inside, so y prime, right, is equal to, now keep in mind with our natural log rules, and here's the whole reason we took the natural log, okay, is so that we would be able to differentiate this, because still at this stage we can't. But remember, by our first law, the natural log of a to the b power is the same as b times the natural log of a. So we can take this ln of x down, and we'll actually end up with ln of x multiplied by ln of sine to the 9x. So now this problem just went from something that was nearly unsolvable to a simple product rule problem. So for our product rule, we're going to have our ln of x multiplied by our 1 over, so it's going to be the derivative of this guy, so the outside, keeping the inside the same, so sine of 9x, multiplied by the derivative of the inside, so we're going to have cosine of 9x, and then multiplied by the derivative of the far inside, which would just be 9. Now I just multiplied all those directly to the top of the fraction to make it a little bit easier space-wise. But yeah, you're just multiplying by the derivative of the inside, so just following the chain rule laws. And then we'll have plus, so ln of x, that will just end up 1 over x, multiplied by this whole mess, so ln of sine of 9x, right? And then we multiply both sides by y, so that we can isolate our y prime. It's going to be this whole thing, I'll go ahead and write it out, times y. Now while I'm writing this, take a look and try to see how this works with the formula that I stated above, and where you think you see the similarities. Alright, so here's where this ties in with the formula. Okay, we have our y prime, just like we do right here. We have our y, just like we do right there, which typically you'll end up replacing with your original y. So we would replace this y with our sine of 9x to the ln of x power. So this guy right here. And then on the inside right here, here's our derivative of ln of y. So what I mean by that is right here when we took the natural log, this was our ln of y, right? Because y is equal to this, and here's ln of y. And we simplified it out, and then we took the derivative. So all this equation is saying is you'll end up with y prime is equal to the derivative of the natural log of whatever your original equation was, multiplied by your original equation. And that's the basis for logarithmic differentiation. Now we'll go ahead and try another example. I want you to give this one a go without me. This one should be a little bit easier. So it's going to be y is equal to x to the 6x power. Go ahead and stop the video now. Alright, so you take the natural log of both sides. So we'll have our ln of y is equal to our ln of x to the 6x power. Oh, now my cursor is drawing a little bit smoother. Alright, and now we can use our natural log to take down this exponent. So we'll have the natural log y is equal to 6x ln of x. And then take the derivatives of both sides. So in this case, we're going to have to do outside, so 1 over y times y prime. Alright, and then here we're going to have another product rule. And that's typically going to be the case with logarithmic differentiation. Whenever you're taking the logarithm of both sides, it's normally in order to bring down an exponent or something of that nature. So you end up having product rule a lot of the time. But regardless, so using my way of doing product rule, so we have our u, we have our v, and it goes u dv plus v du. So in this case, we're going to have, we'll just bring out that 6 to the very outside to make it a little bit easier on ourselves. So we're going to have u times the derivative of v, so 1 over x, plus v times the derivative of u, which would just be 1. So to isolate y prime, we multiply both sides by y, so you get y prime is equal to 6y, and then x times 1 over x will just be 1, plus ln of x. And if they want it all in terms of x, to finish off this problem, you replace y with our original y value, so you'd get 6x to the 6x times 1 plus ln of x. Alright. So now this last one's going to be a little bit of a challenge problem. So go ahead and try this one. Stop the video right when I finish writing it, but this one will be decently difficult. But it's just another example of how you can make your life a little bit easier with logarithmic differentiation. And what's nice about this example too is it's not the typical, you know, I need to bring down an exponent that I can't take the derivative of. You know, this one is just one that would be a messy product rule with lots of crazy chain rule, and we want to go ahead and simplify that out for ourselves to make it a little bit easier. So you'll start by taking the natural log of both sides. So we get the natural log of this whole mess, right? And now you may see a few things here. For one, and where we want to start, is that we have 3 separate terms all multiplied to one another. So we can actually separate that out using our additive product rule for the natural logs. So in other words, that's our natural log of AB is equal to the natural log of A plus the natural log of B. So this will be the natural log of square root of x plus the natural log of e to the x squared plus the natural log of our x squared plus 3 to the 7th power. Alright, perfect. So the way we're going to do this now to further simplify is using our exponent rule for our natural logs. So that is that the ln of a to the b power is equal to b times ln of a. Right? So where we're going to start is going to be right here. So remember that the exponent for a square root is 1/2. So we can rewrite this as 1/2 natural log of x. So if this was x to the 1/2 power, we pulled down that exponent following this rule right here. That a looks horrible. That looks even worse. Alright, now for ln of e to the x squared, now this would be the same as saying e to the x in parentheses squared. So we're going to bring down just that square because we know how to take the derivative of an e to the x easy. In fact, actually, let's just scratch that whole thing that I just told you. Because one other fundamental law of logarithms that we did not go over is that natural log and e cancel each other out. So if you take the e of a natural log, you'll end up with just the insides of the natural log. And if you take the natural log of an e, you'll just end up with the exponent on the e. So this actually completely disappears, and you're left with x squared. Alright, and then right here, so we have our exponent right there, so we can pull out that 7 and make it a 7 natural log of x squared plus 3. And now we take the derivative of both sides. So keep in mind, none of these laws or rules replace taking the derivative. You still have to take the derivative. All we're doing is setting it up to where it would be easier for us to do so. So if we take the derivative of the left side, we'll end up with 1 over y times y prime. So that's our outside, inside. Right here we have 1/2. So that's just a constant. So the derivative of ln of x would be 1 over x. So we'll end up with 1 over 2x. Right here, it's just simple power rule, become 2x. And then our 7 is going to stay constant. This will be 7. And then the natural log, we're going to have to think outside, inside, right? So this will become 1 over x squared plus 3 multiplied by the 7. So we'll just put it straight there on the bottom, x squared plus 3. And then multiplied by the derivative of the inside, which would just be 2x. And then this would be our final answer. So I hope this helped somewhat. I'm having some trouble with the new board, kind of lagging whenever I'm recording the screen, so I'm going to figure that all out. So please excuse it. But good luck.